Hello, dear students. Today we have Proposition 9 of Book 3. If there be a circle and a point be taken, and you drop lines from that point to the circumference of the circle, and more than two lines be equal, that point is the center of that circle. Here we have a circle, here we have a point, and here we have three lines dropped to the circumference, and we have those three lines being equal. That's the given. Thus, it is required to show that this is the center of the circle. Okay, let's talk about Proposition 1 for a while, because we're going to use that from our bag of knowledge. Remember, Proposition 1, starting off the book, said let's find the center of the circle. And it did so by taking a random line, bisecting that line, then drawing a line from that point of bisection, a line at right angles, and then carrying it through to both sides. And then it bisected that line, carried through at a certain point. It bisected that line. And then it was a reductio saying that will be the center of the circle, that point of bisection on that line so drawn. For if not, etc. And it took another point, and then it connected these points, and it did side, 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 and showed that these two angles would be equal to each other, right angles. So this is a right angle, and this is a right angle, so this equals this, the whole to the part, which is ridiculous. So that's not the center, neither is that, that must be the center. Now, we didn't talk about it, that's why I'm explaining all this. There's a corollary. A corollary in a proposition is something that becomes manifest by the very act of this demonstration. And that what's the corollary to this prop? That if there be a line in a circle, and it be bisected, like we did, and a line drawn at right angles, if there be a line at right angles from a certain line, that line drawn at right angles, the center of the circle will be on that line, okay? So that's what we're gonna do over here. Here we have the three lines that is required to show that this is the center of the circle. Let's do that by... Now that Bern website with all the colors, that does a reductio, and I don't know why they did that, but that's not Euclid. You got to do this not through a reductio, okay? So let's see if this blue one works. Let's do this one. It's not working. This one will. Good. Okay, so let's bisect both of these. Bisect this one and bisect this one. And let's connect that point of bisection with that original point, and connect this point of bisection with the original point, okay? So here you have this triangle and this triangle, this being bisected, so this is equal to this. And this is common, so you have two sides equal to two sides respectively, and the bases are equal because they're radii of the same circle. So the angles which those bases subtend must be equal. So this must be equal to this, and therefore they are right angles, because if you have adjacent angles equal to each other, they're right angles, okay? And so we know from the corollary of this proposition that if a line be bisected and a straight line be drawn from it, from right angles in a circle, then the center of the circle will be on that line so drawn at right angles. Let's do the same thing over here. We have two triangles. We have this being equal to this because this was bisected. We have this drawn at right angle. No, we have this connecting here, so we have two triangles such that this and this are equal to this and this. This side and this side are equal to this side and this side. And the base is equal to the base because they're radii of the same circle. So we know that the angle opposite those bases, or the bases of which they are subtending, the angles of which they're subtending will be equal. So this angle is equal to this angle. And then therefore they are right because you have adjacent angles equal to each other. They're always right angles. So here you have a situation where you have a straight line's been bisected and another straight line drawn from it at right angles. Therefore that center of the circle, we know from the corollary of Proposition 1, Book 3, we know that the center of the circle will be on that line. And when we could actually do that, we see that there's only one point in which the red line and the blue line intersect. So if the center of the circle is on this red line and the center of the circle is on this blue line, and there's only one point of intersection, and it's that original point because we connected these 2 points to that original point, so that original point must be the center of the circle. Therefore, we have shown that if there be a circle and a point be taken at random, and it so happens that lines, more than 2 lines falling from that point are equal, that point so taken must be the center of the circle. Quod erat demonstrandum. Thank you. Bye-bye.